Alright everyone, welcome back. Today we're discussing the flexibility method, which is the inverse of the stiffness method. And stiffness method is really what we talked about in the last two lectures. So let's just quickly recap on what we did. With the stiffness method, we introduced truss and beam elements. And if I were to introduce a truss element again, and this time increase the length of my element by u. So we have this deformation with a magnitude u. I could use a parameter which we called stiffness, k, which we multiplied with the u to give us the force that's necessary to obtain such deformation. And this was p. So for axial elements, we ended up finding that the stiffness is equal to EA over L. That is the elastic modulus, the area of the axial element, and the length of the axial element times u. And usually stiffness has units of force divided by displacement. And so when we discussed flexibility being the inverse of stiffness, the units will end up being displacement divided by force. And what I'm going to talk about now is what flexibility matrices are. So with flexibility matrix, we end up with the same two indices that we ended up for stiffness matrices, but this time I is referring to delta I, so a deformation at location I due to a unit value of force at location j, so we call that Pj. And this relationship can only be defined and derived for elements that are stable. So if I give you an element, if I give you this mass, or perhaps this beam that was sitting on two rollers, so this is a beam that's sitting on two rollers, and I tug on this roller setup with a force P. There is nothing there to resist the lateral exertion of P. And so this element can move and have a rigid body motion. This is what we call a rigid body motion. And in such cases, we cannot obtain the flexibility matrix. The flexibility matrix is non-existent. And what this means is that the inverse of the stiffness matrix does not exist. So we said flexibility is the inverse of the stiffness matrix, so K inverse. And for this to exist, K must be non-singular. So the inverse of K must exist. And anytime the inverse of K doesn't exist, meaning the determinant of K is equal to 0, we have a scenario of singularity, and the flexibility method does not exist. And the rigid body motion is an example of that. Okay, so we render this or call this unstable. And for such cases, flexibility doesn't exist. Okay, so let's talk about the slice flexibility method. Here it is. So in this example, we're going to have a truss element, and this truss element will be fixed on the left-hand side. So we're going to fix it on the left-hand side. And we're going to have axial, lateral, and rotational forces applied at the very tip of the truss element. And so what we're interested in is finding out how these axial and the lateral and bending forces end up at some slice somewhere in the span of this truss element. This is a slice. Okay, And this slice has a very finite length. We call it dx. We're going to measure x from the left-hand side. That's x. And what we're going to end up with is, if we were to cut this element at the location of the slice, is the following. We're going to have, oops, here we are. We're going to have our slice, which has a length dx. We're going to have our boundary condition, which was fixed. And we're going to have a new set of forces at the location of the slice. And we're interested in finding out what these forces are. And so my forces at the slice, I'm going to refer to them by PS, are equal to some transformation matrix Vx multiplied by the original forces at the very right-hand side. So let's call this relationship number 1. So again, PS is the force acting at the location of the slice. I can also say that du is equal to Vx transposed dus. du is some very tiny deformation, and dus is the tiny deformation at the location of the slice. And we use the same transformation matrix, but this time it will be transposed. So we call this relationship number 2. And there's going to be a third relationship which connects the two parameters slice deformation with the slice forces. So we have some flexibility element, some force element, and dx. So when I combine all these, this is relationship number 3. When I combine 1, 2, and 3, I get the following. I get u to be equal to, and this time u is a vector, integral length Vx transpose, Vx being the transformation matrix, dus. When I plug in the values for dus, I get the following. I get the Vx transpose Fs Ps over dx. And lastly, I'll plug in relationship number 1 for Ps, and that will give me the following. Okay? So what I'm doing here is I'm finding my total deformation as a sum of deformations, tiny deformations, in every little slice along the span of my beam or truss. And that's really how we're going to formulate the flexibility matrix. Let's do an example. In this example, we're going to look at a simply supported beam. And this simply supported beam will be drawn with this line here. Okay. And so we have a pin support and a roller support. And we have the following degrees of freedom. I'm going to call this one 1, call this 2, and call this axial 1 3. In the last 2 lectures, we have always ignored the axial element, but this time we're not. We're going to use it. And with this simply supported beam, I'm going to cut a slice here in the middle, And at the location of my slice, I know I'm going to have some moments. Oops, there we go. I know I'm going to have shear forces. And I know I'm going to have lateral forces. For the sake of this example, I'm going to call these lateral or perhaps axial because they're in the axis of the beam. I'm going to call these V. Or perhaps I should call them N. N is for axial. And I'm going to call these shear ones, the vertical ones, V. Because shear is always referred to by V. And what I'm going to do next is to draw a free body diagram. When I draw a free body diagram, the first thing that I notice is that because I have this P3 applied here, and because I have the N applied here, I know that N is equal to P3. I also have a P1 here and a P2. And so I can simply apply the shear forces that are holding these bending forces, these bending moments back, which are in the inverted direction. So these bending moments are turning my beam counterclockwise, and my shear forces are acting to counteract and hold my beam in the clockwise position. And so if I were to calculate these shear forces or these reaction forces, what I would get are two values, P1 plus P2 divided by L, and I would also get P1 plus P2 divided by L. And so if I'm looking at my shear forces, in the form of a shear force diagram, what I can do is the following. I need to draw my forces going up here on the left hand side. They're going to go flat across and then go back down. And what I have here are the VFD. I need to draw a BMD later on. And this is my VFD diagram. And the magnitude here is labeled as P1 plus P2 divided by L. What I'm going to do next is to draw a second line. This time it's going to be for bending moment diagram. Here it is. And my bending moment diagram will be kind of like that. Here it is. Perhaps I should draw it in a different way, kind of like that. There it is. All right, now what I would get at the locations here and down here are two values. I will have m is equal to minus 1 minus x over L, P1, plus x over L, P2. Here it is. And so what I can simply do is to connect my slice forces, so the axial one, the shear one, and the moment, with the forces that are applied at the locations of the boundary conditions, and I'll get the following. So a 0 here and a 0 here. And so I obtained this matrix, and I'll explain in a second what this matrix is. I have a P2, P3. Okay, this matrix is transforming the forces that are at the locations of the boundary conditions to some arbitrary force at the location of some arbitrary slice. And so this is the transformation matrix that we were talking about earlier, and we denoted it by Vx. So that's what that is. At the same time, I'm going to have a slice flexibility matrix that has the following properties. Excuse me. 1 over elastic modulus times the area. 0, 0. It's going to be diagonal, so I will have zeros in the off-diagonal terms. 1 over the shear modulus, A prime. Here, A is referring to the area of beams that carry the shear force. So typically when we have a beam, like an I-beam, most of the shear force is carried by the area here in the middle. These locations don't really contribute much. So if you were calculating the A prime, this is what you would be looking at. Whereas A would be the entire area. And so we have a 0 here, another 0 here, and I have a 1 over EI. And that's taking care of the rotational and flexural components. Okay, we're going to close that up. So now if I'm interested in the flexibility matrix for this simply supported beam, what I would have to do is to integrate. So I have my flexibility matrix, and I need to integrate. I have a L0. I need to put down my Vx transposed, which is minus 1 over L, x over L minus 1, 0, 1, minus 1 over L, 0, 0 here, and that's an x over L. So that one is Vx transposed. I also know my slice flexibility, and I also know what Vx is. And so when I integrate this, I get the following values. People often prefer to ignore shear deformations because they tend to be small, and you can do that. And if you intend on doing that, just let the shear modulus be 0, and what ends up happening is all these terms go back to 0. So you're only going to look at deformations due to flexural components and axial components. 3i plus g a prime L. You could also assume that your shear area is equal to your complete area, so your normal area. That's actually true in most instances, except a few. Okay, so we close this up, and we have simply obtained our flexibility matrix. And now if I know what my forces are, I can easily multiply it by this flexibility matrix and obtain my deformations. So let's do an example. With this example, I'm going to look at a non-prismatic beam. So in this case, I have a beam that has sectional properties that are changing in a continuous way. They're kind of tapering up. So up here, I have my beam sitting on a pin support, and up here I have a roller support. And at the very left hand side, I will say I have properties that are A naught, A prime naught, and I naught. A prime naught is the area for the shear, A naught is the area for the axial deformation, and I naught is the moment of inertia. And I've got this neutral axis that's going through my beam and has these values. And there's also a length L. I'm going to be measuring X from the left hand side, and what's going to happen is that my beam will have an initial vertical height of h naught and the final vertical height of alpha h naught. And so if I were to describe the change in height of my beam over x, what I would have is the following. So for any value of alpha, I can describe the depth of my beam, or the vertical height of my beam. I can do the same thing for the area. And I have the following. And lastly, I can do the same thing for the moment of inertia. As a function of x, it will be I naught for this particular example, I choose to ignore shear. So what I'm going to do is I'm going to let A naught prime to equal to 0. And by doing that, I'm going to fully ignore the contribution of shear towards deformation in this structure. And I also have the area equaling 100 inches squared, the elastic modulus equaling 29,000 psi, and the moment of inertia equaling 900 inches to the power of 4. So when I plug in all these values and I integrate, if you remember, we had a flexibility integration equation, and we went from 0 to L. I need to integrate, plug in all these values. What I end up getting is the following. And flexibility matrices, just like the stiffness matrices, will end up becoming symmetric. So what I can do is to just fill out the upper triangle and ignore the bottom one. All right, I'm going to have symmetry down here. And so, oh, there's also a 10 to the power minus 4 here. So I'll forget that. And so now for any kind of forces that are applied on my non-prismatic beam, by the way, let's write that down. Non-prismatic. So any forces that I'm going to have on my non-prismatic beam, what I can do is simply to write that deformations are equal to the flexibility matrix times some sort of some externally applied force, P. So P is a vector, U is a vector, and F is a matrix. Okay, so that's really it. This is the flexibility matrix, or the flexibility method, and that's all you need to know about it. There are, of course, more advanced examples that we're going to look at, hopefully in future lectures and future courses. But for the sake of this course, which is Structural Analysis 1, this is where we're going to limit the flexibility method to. I'm going to have one more lecture in this lecture series, and that's going to be a more advanced example on structural analysis using the stiffness method. And with that, we're going to wrap up this course, and hopefully the next the next course that I'm going to work on will be a course on dynamics. So I look forward to reading some of your feedbacks, comments, and hopefully I'll see you in the next lecture. Take care.